In our last video, we talked about properties of waves, types of waves, and the different parts of waves. And today we're going to look more closely at sound waves. Sound waves are basically pressure variations transmitted through some kind of a matter. If you look below at the picture, you see a speaker that is sending sound to the receiver, which in this case is an ear. Between the speaker and the ear, you see some air molecules that are densely compacted, some air molecules that are spread out. And so that pressure variation between the sender and the receiver, that pattern of compressions and rarefactions, is what the sound receiver, the ear, picks up as music, as sound. So in between the two, yesterday we talked about types of waves, how some waves can travel without a medium, those are electromagnetics, how some waves have to have a medium, those are mechanical waves. Sound is an example of a mechanical wave. It has to have a medium. There has to be some kind of pressure variation between the molecules, whether those are solid, liquid, or gas, that is transferring that energy from one place to the other. We also classified waves yesterday based on whether they vibrated perpendicular to the way that they were traveling or whether they vibrated parallel to the way they were traveling. As you can see from these compressions and these spread apart areas, these rarefactions, sound is a compressional or a longitudinal wave. The vibration is parallel to the direction that the wave is moving. So we're going to look deeper today at sound waves and at how sound behaves. Now keep in mind, a lot of these properties that we're going to talk about today, even though we're putting them in the sound section, a lot of these properties are shared by other types of waves, and we'll mention that as we go, but we kind of closely associate some of these with sound specifically. So first is loudness. How loud or how quiet a sound is depends on the amount of energy that we give it, which is directly tied to the amplitude of the wave. So down here we have loudness of sound represented actually in a transverse wave because it's kind of hard to see the difference between compressions and rarefactions. Keep in mind sound is a longitudinal wave, but you can see with low volume you have very little energy, you have less air pressure, and so instead of small highs and lows, small amplitude, you would have actually less compacted compressions and more compacted and more spread out rarefactions. With high volume, more air pressure, you get a louder sound. You have more of a difference between the highs and the lows in this picture. In practical application, more of a contrast, a difference between the compressions and the rarefactions, between the high pressure areas and the low pressure areas. And that's why when you get some sounds that are too loud, freight trains and jackhammers and things that are way too loud, thunder, it actually hurts because you've got so much pressure pushing on your eardrums that it causes actual pain. Too much energy can be an unpleasant thing. Another thing that we equate with sound is pitch. Pitch is how high or low the note sounds. And the pitch that we hear is related to the frequency of the vibration. Something that has a very high sound has a very high frequency. The wavelength is very short. You can see in this picture between the speaker and the ear, again, the very top line is a very high frequency, short wavelength, high pitch sound. The bottom one has a very low frequency, a very long wavelength, and will be perceived to our ears as a very low sound. So I have with me today my flute from high school and college, and this is a musical instrument. All musical instruments work kind of the same way in that what you're doing with all the buttons and all of the different doodads is you're changing the wavelength of the sound that you're producing. So if I play kind of a low sound, the sound that I create is based on what I'm pushing, what keys I'm pushing in this flute. If I change the buttons that I'm pushing, then I change the length of the barrel of my instrument. In a trumpet, you would do this with different keys. In a trombone, you might actually slide the slide out. But you're changing the length of the barrel of the musical instrument. So if I change it, you hear a different pitch of sound based on how long I've made the instrument or how short I've made the instrument. Piccolos are very closely related to flutes. Those are very short. You hear very high pitches with a piccolo. So all musical instruments basically work off of creating different wavelengths of notes, which affect the frequency, of course, which we perceive as different pitches. Sometimes, though, with a marching band and with daily life, you get waves that are trying to get into your ears at the same time. You have multiple things that are trying to occupy that space and get your ear's attention. When you have two waves in the same place at the same time, that interaction between the waves is called interference. Interference can be a good thing or it can be a bad thing. When you have the waves matched up perfectly, when you have the crest of one and the crest of another and they line up perfectly, then they add together and they combine. So if we had two flute players here that were both playing the same note at the same time and that were in tune, of course that's a big one there, that were in tune, then our two sounds would combine together and you would hear a louder sound. You'd get more amplitude. However, you can also have sounds that are canceling each other out. If I were playing one note and the other flute player were playing a different note, or maybe they were just out of tune, at some point our frequencies and our wavelengths would add up together. We'd have crest and troughs at the same place. We'd have compressions and rarefactions actually at the same place. At other times, they wouldn't quite line up. And where you have a compression and a rarefaction kind of fighting with each other, then they end up canceling each other out and you would hear something actually softer. Those of you that are in band or in choir, you know that one way that you can tell if you're in tune with the person next to you is listening for the beats. Beats would be kind of a wobbly sound. If you're out of tune, you might be playing the same note, but you might hear a wah, 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 wah sound. That wah wah is that difference in sound, in amplitude, in loudness, that difference in loudness caused by constructive and destructive interference happening over and over. The best way to fix the wah 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 is to get in the same pitch so that your wavelengths add together. They're at the same place at the same time. So here's the two types of interference, constructive and destructive. If your amplitudes are in the same direction, they'll add together. You'll get one big sound. With destructive interference, if they're in opposite directions, they'll completely cancel each other out. And of course, if they're not quite tuned up, then you get kind of a combination. You get a little bit of canceling out at times, you get a little bit of constructive at times, and that's what that gives that pulse. But sound is not the only wave that interferes. We talk about interference here because it's easy to hear interference, but you can get light wave interference, you can get even ocean wave interference. If you've got lake waves and then a boat comes by, you might notice that at times the waves that are the combination of the boat waves and then the wind waves, they might be taller at some points and might be less tall at some points, but you can get that interference, constructive or destructive, with any type of wave. What we're trying to create with musical instruments are pleasing things called standing waves. With standing waves, you get like let's say for a guitar, for instance. It's really easy to see in the picture below. Imagine the string of a guitar. When we pluck the string of a guitar, you get points at which the wave that you send down is being reflected back. And if you have it at just the right wavelength for that string, they interfere constructively and destructively perfectly so that you get what's called a standing wave. You get these nodes that don't move at all, and you get these antinodes which have the biggest displacement. And these are what you're looking for when you're creating music, is a nice standing wave that gives you a good sound without that constructive, destructive interference. And so when you get that perfect spot, that perfect wavelength for your guitar string or whatever you may be using, you get this tendency called resonance. Resonance is the tendency of a system to oscillate with a greater amplitude at some frequencies than others. For instance, tuning forks. I'll show you some tuning forks. You have tuning forks that are set to resonate, to vibrate at certain frequencies and create certain notes. When you tune the head of a drum, when you're trying to make a drum that you hit sound a certain way, you stretch it or you release it until it vibrates at the frequency that you're wanting. All objects, though, will vibrate. You can hit the leg of your desk and it will vibrate and create a sound. That frequency that your object just naturally vibrates at is its resonance point. And finally, the Doppler effect. This is one we've all heard, and you might not have really known what it was, but the Doppler effect is the change in apparent frequency. That's the frequency that we perceive, what we hear, due to motion between the source and the receiver. Sometimes it could be the source moving, like if you've ever stopped on train tracks and you hear the train coming, you hear the yum as it passes you. That high pitch as it's coming towards you is followed by a low pitch as it moves away from you, ambulances, whatnot. So it could be the object is moving, or it could be that you're moving. I have been moving past an object before and maybe passing something that has a radio playing, and as I pass it, the sound goes from a really high pitch to a really low pitch. The reason for this, the reason that it sounds different as you pass, is called Doppler Shift. You see here in the picture, the top picture, you have a train that's sitting stationary. It's just emitting a sound like without any kind of change in that frequency, just bah. As the train moves though, ahead of it, that air that it's emitting, the sound that it's emitting that's compressing the air, is compressed more than it normally would be, because not only is it emitting the sound waves, but it's also moving towards the direction that it's emitting those sound waves. On the back end, it's emitting the sound waves and moving away from the sound waves that it's emitting. So you get a shorter wavelength, higher frequency sound on the front end where you're moving towards, and then on the back end, you end up with that sound stretched out, a longer wavelength, which gives you a lower frequency, which you hear as a lower pitch. So Doppler shift is one of those things that we just kind of don't get why that happens, but it's all about the waves and the compaction of the waves. So next time you're watching NASCAR and you hear the yum, yum of NASCAR races, think about that. That's Doppler shift. As the cars are coming to you with their big loud engines, that sound is being compacted, shorter wavelength, higher frequency, higher pitch, and then as they're moving away, you end up getting that stretched out sound, that longer wavelength, that lower pitch, lower frequency. You can see actually with the two circles, they talk about blue shift and red shift. Blue shift, you end up getting things that are more compacted. Red shift, you get it more stretched out. The reason why we call it blue and red when we're talking about sound is that sound is not the only thing that can be Doppler shifted. You can actually get a Doppler effect in light too. Blue wavelength of light is shorter wavelength, higher frequency. Red wavelength of light is longer wavelength, lower frequency. So if you have, like, say, a star, if you're an astronomer and you see a star that at times looks bluer, more shifted that direction on the spectrum, and then other times is more red shifted, more towards that end of the spectrum, not necessarily red, but red shifted, longer than it should be, or blue shifted, shorter than it should be, then you can kind of get a feel for the fact that the star is wobbling. Sometimes it's coming to you, sometimes it's going away from you. So light will also have a Doppler effect that we can use in astronomy. It's probably not going to be noticeable as you're driving past a, street light, but on something this far away, it's a really useful tool to help scientists understand what's going on in the universe. So that's where we're going to stop. We're going to pick up next time with light and the electromagnetic spectrum. And don't forget to take the quiz at the end. Have a good day.